Let me begin with an overview of what this series of lectures is going to be about. It's going to be about arithmetic applications of the concept of pseudorandomness, as the title suggests. So I'll start with the discussion of Fourier analysis. In vector spaces over finite fields. So it will turn out that looking at Fourier coefficients is in close analogy with looking at eigenvalues of graphs that were discussed in David's talk earlier. And perhaps it's not surprising that Fourier analysis will give rise to a good measure of quasi-randomness or pseudo-randomness in arithmetic problems, just as the eigenvalues gives a good measure of quasi-randomness in graph theory. So I'll start with an overview of basic Fourier analysis. And the rest of the lectures will be mostly focused upon how to use Fourier analysis to actually tackle arithmetic problems. And an important tool to achieve this is what's called the regularity lemma. Now, because I'm talking about the arithmetic aspects, I will be talking about the arithmetic version of the regularity lemma. So in David's talk earlier, you have heard the word Zemurelli's regularity lemma in graph theory. This is the arithmetic version of that regularity lemma. And applications of the regularity lemma. So this is basically the plan for the first two lectures. And in the third lecture, Julia will talk about something about the theory of Galois norms. So it will turn out to be the case that using the theory of Galois norms, one can get a stronger notion of pseudo-randomness compared to the basic Fourier analysis. And this stronger notion of pseudo-randomness is important for understanding certain problems. So in fact, it will turn out to be the case that Fourier analysis is more or less the same as studying Galois U2 norm, but things become different when k is at least 3. So I will talk about the U2 case of the theory of Galois norms in this first lecture. So she will talk about Galois UK norm and regularity lemma and applications. And finally, in the last lecture by Tom Bloom, he will talk about some cool recent developments in this subject. In particular, the results last year by various people on the CAPSAT problem using the polynomial method. Okay, so that's the plan. And to start with everything, I'm going to just fix some notations. So in my talk, the capital G will always be a finite abelian group. Rather than a graph. So in particular, it will just be the following finite abelian group. We will work in what's called the finite field model. So we'll work in F2 to the n. So There's something called the finite field philosophy in additive combinatorics. So as you may know, in number theory and combinatorics, a lot of the times we would be interested in the group G being the cyclic group, Z mod n, for example. Now, F2 to the n is in a lot of ways different from Z mod n, but it has a lot of structure, such as having a lot of subspaces, which means that doing things like Fourier analysis is a lot easier in a finite field model. And the finite field philosophy is saying that let's figure out what happens in this model setting, and then if you're a number theorist like me, you can try to translate the method back to the cyclic group setting. But I know that a lot of the audiences here are computer scientists, so to make friends with them, I'll work entirely in this F2 to the n. So F2 to the n is just 0, 1 vectors of length n, and you add 2 vectors by component-wise adding modulo 2. Okay, so before starting with telling you about what Fourier analysis is, I just want to tell you about the application that I'm going to discuss later in the course. So this is what's called the arithmetic removal lemma. So if you're from combinatorics background or theoretical computer science background, you may have heard of what's called the triangle removal lemma. This is exactly the arithmetic version of it. So let me state it. So let A be a subset of G. Suppose that if the number of solutions to the equation A1 plus A2 plus A3 equals to 0 with the 3 variables in the set A is small, more precisely little of n squared. So I will always write capital N to be the size of the group G, which is just 2 to the little n. So if the number of solutions is small, then one can remove a small number of elements. One can remove little of n elements from A to obtain a set A prime, so that there is no solution to that equation in A prime. So by the way, can everybody see what I write and hear what I say? Okay. So this will be something that will prove after establishing what's called the arithmetic regularity lemma. So just a bit of history on this and also on the graph analog, a triangle removal lemma. So the triangle removal lemma is an important tool for computer scientists because it's useful in property testing. And this arithmetic version is first proved by Green in 2005. Using an arithmetic regularity lemma that I'm going to present. But later it was discovered by Krau, Sarah, and Vina that this can be deduced from the triangle removal lemma. The reason that was important is that the fact that this can be deduced by the triangle removal lemma is that the deduction works no matter what the finite abelian group G is. So the proof I'm going to present here only works in G equals to F2 to the n. And in general, the proof becomes much more difficult and complicated, even more complicated than the proof of the Zermedi regularity lemma in graph theory. Okay, So this is the theorem that will hopefully be proved towards the end of tomorrow's lecture. And hopefully that's enough motivation for you to listen to what the part 1 and the part 2 is going to be about. Okay, so I'll start with Fourier analysis. I suspect that some of you are already familiar or either experts in this area, but I'll just go over them nonetheless. So more precisely, Fourier analysis on this f2 to the n. So f is always going to be a function on G, complex valued function. And so define its Fourier transform f hat, which is again a function, by the following. So I'm going to write it down and explain the notation. It's going to be the inner product of f with a character. So writing it out, this is the average f of x minus 1 to the dot product of r and x. Okay, so here, first of all, the dot product is just the dot product on f2 to the n. And then this average notation is average. So the number of elements in the sum is capital N, so it's 1 over n times the sum. So this explains this line of definition. And they are the same because this notation means that I'm taking the inner product between this function f and that function which is the linear character. So yeah, the inner product is defined in this way. So one just general remark about notation, normalization issues regarding Fourier analysis. So in summary, the following 2 sentences are going to be valid. We're going to basically use the probability measure on physical space, in the physical space, and the countermeasure in the frequency space. So here R is considered as a frequency, so I'm considering f as a function of physical space and the Fourier transform f hat to be a function on the physical space. The probability measure is the measure that assigns the total mass to be 1, and the counting measure is a measure that assigns each element to have measure 1. So in particular, just to make sure we understand, when I have 2 functions f and g on the physical space, and when I use this to indicate their inner product, it is going to be defined with respect to the probability measure. So it's the average. So this is why this inner product is this average. On the other hand, when I'm looking at Fourier transforms of 2 functions, f hat of g hat, and I will use the same notation, inner product, is going to be defined in terms of the counting measure. So this would be a sum. This is going to be useful when we write down some basic identities involving Fourier analysis, so that you don't need to remember anything about normalization factors. They will always be incorporated into these 2 conventions. Okay, any questions so far? So let me just state some basic properties about the Fourier transform. So all of these basic properties follow from the orthogonality relation. So here is the orthogonality relation. So I take the character defined by R and average the value of it across the whole group. I get either 0 or 1, depending on whether the character is trivial or not. So if I is 0, then everything is 1 and the average is 1. If I is non-zero, then everything cancels out and the average is 0. So it's a relatively straightforward exercise to prove what I'm about to write using the orthogonality relation. So lemma. So first of all, we have the Fourier inversion formula. You can recover the original function in terms of its Fourier transform. Okay. So again, this sum is happening on the frequency space, so there is a sum here. And then we have the Plancherel identity. Which is saying that the Fourier transform operator is in isometry. So the inner product between f and g is the same as the inner product between f hat and g hat. So perhaps I'll say this for the last time, the inner product here and here are defined differently. As a special case of Plancherel identity, you have the Parseval identity. The L2 norm, so this is what I said. The L2 norm of f hat is the same as the L2 norm of f. So this is more or less similar as the result in about eigenvalues, that the sum of the squares of the eigenvalues is the same as the number of edges. So they are related. And finally, about convolutions. So the convolution of the Fourier transform, the Fourier transform of the convolution is the product of the Fourier transform. So let me just remind you what the definition of the convolution is. So the convolution of two functions is a function defined by f star g of x is the average of y, f of x, g of f of y, g of x minus y. Okay, so convolutions occur in a lot of the arithmetic problems, and that's why this is important. So I believe that's basically all I need to say about Fourier analysis. At this point, let me give you a rough form of what the regularity lemma looks like. The regularity lemma is basically a decomposition theorem. It decomposes an arbitrary function f into two pieces. A structured piece and a pseudorandom piece. So of course, what is meant by structure and what is meant by pseudorandomness need to be chosen carefully. So the rough philosophy is that the pseudorandom piece needs to be pseudorandom enough so that for the problem you have at hand, this is basically like a random object. And you would then figure out what the structured piece can look like, and then analyze the problem with the structured piece. In the regularity lemma I'm going to prove tomorrow, the structured piece will start with the pseudorandom piece. The pseudorandom piece will be functions that have small L infinity norm in the Fourier transform. So these are functions with small L infinity hat norm. So you can compare this with the analogy in the graph lecture. So in the graph lecture, quasi-random graphs are those graphs with small lambda. So the second largest eigenvalue roughly corresponds to this norm, and this makes sense. And it turns out that a good notion of structured piece in this case is going to be functions that are constant on cosets of a large subspace. So just to have the picture in mind, you have a subspace of f2 to the n. So I will always use this notation to denote a subspace, no matter what the subspace is and what it really means. So, and you have its cosets, okay? So a structured piece is a function that's constant across in each circle. But it could be different constant across different circles, across different cosets. So this is the rough form of what the regularity lemma will look like tomorrow.
So you just going to write f equals f1 plus f2 or something like that? Just that when you say decomposes,
yes.
You're saying it additively.
Yes, exactly. So thank you. So when the regularity lemma decomposes an arbitrary function f into the sum of these two pieces. Thank you. Any other questions?
So just for my intuition,
Yeah.
so if you choose a random function,
Yeah.
in the frequency domain it'd be just pretty flat.
Yeah.
Right, okay. So then we're calling something pseudorandom if there aren't any spikes, if it's pretty flat as well.
That's a good question. So if you consider yourself, if you choose the arbitrary function on the physical space, say -1, 1 valued, okay, you have a trivial bound for all of its Fourier coefficients, which is bounded by 1. But if your function is truly random, then with high probability, all of these Fourier coefficients will be little of 1, which means that they have small L infinity hat norm. So these truly random functions are indeed pseudorandom, which should match the intuition. Okay, so now before stating the precise form of the regularity lemma, I do want to give a quick introduction about the theory of Galois norms. So this was, as the name suggests, first introduced by Galois around 2000 in his proof of in his Fourier and harmonic analysis proof of Zemuredi's theorem about finding long arithmetic progressions in dense sets of integers. So it's sometimes also referred to as the uniformity norms, and that's why the U is used there, I suppose. So I'm going to define what it is in general, but then I'm going to focus on the U2 norm and tell you about the relations between the U2 norm and Fourier analysis. And in the third lecture, Julia will say something about the higher Galois norms, which corresponds to what's called the higher order Fourier analysis. Okay, so before I make the definition, I just want to say one thing. We say that f, a function f, is one bounded if it's bounded by 1 pointwise. So from now on, we will almost always just focus on one-bounded functions, although sometimes it's not necessary. Okay, so a piece of notation. So for a shift, for some h, we define the operator delta h by the formula. So delta h is going to be an operator that acts on functions. So if I have a function f, the operator delta h acting on f will produce a new function delta h of f, and this function is defined by the formula f of x plus h, f of x bar. You should think of it as a multiplicative derivative of the function f in the direction h. So, definition. The UK norm of function f is defined by so its UK norm is defined by the formula that the 2 to the k's power of this UK norm is equal to the average over x, h1, h2, hk, delta h1, delta h2, delta hk, f of x. So these are these k operators applied iteratively. So I'm just going to write down explicitly what this is for k equals to 2, so that easier to digest if you haven't seen this before. So if you apply the definition of the delta operator, the U2 norm is defined by the force power being equal to the average over x, h1, h2, and then the following product: f of x plus h1, f of x plus h2, f of x plus h1 plus h2. Okay, so this explains why there is a force power here, because you have the product of 4 shifts of f. And a simple fact is that, first of all, this is well defined in the sense that the right-hand side is always a non-negative real number. And second of all, it indeed gives a norm for k equals to 2. Sorry, for k at least 2. So geometrically, in the U2 case, what happens when you range over all values of x, h1, h2 is that these 4 arguments, x plus h1, x plus h2, and then x plus h1 plus h2 form a parallelogram in 2 dimensions, and you're averaging over all of these parallelograms. So you can do the same thing for higher UK norms, and they will correspond to higher dimensional parallelepipeds. A question about the definition? Yeah.
So the structured pieces, is this the same as the low-degree polynomial?
So yeah, exactly. So in this case, a structured piece is exactly a degree 1 polynomial, and you have to put some bounds on the coefficients as well, I think.
But this does not exclude the small L infinity norm, right? I mean, these 2 pieces are not excluded with each other.
So it's certainly possible for a function to be both structured in this sense and pseudo-random in this sense. But I'm just saying that any function can be decomposed in this way. So for example, if your function is both structured in this sense and both having small norm in this sense, you can just say it's 0 plus that function. And this is still good. So the point being that as long as you can analyze the structured piece usefully, and also show that the pseudorandom piece looks like a genuinely random piece for your problem, then such a decomposition should work in your application. Yeah.
So, for example, the zero function also satisfies this definition of pseudo-random, right?
Yeah.
But it seems like it's clearly, not pseudo-random, right?
So, so I should say that the name pseudorandom should basically, let's forget about random for a moment and just look at the word pseudorandom. The reason this comes up is that for a lot of the problems, you expect the theorem to be true for a random object with high probability. And I think the word pseudorandom in this context is usually cooked up so that you have a deterministic object, so that when the pseudorandomness condition, such as this one, is satisfied, then the theorem holds. So for a lot of the arithmetic problems, the constant function 0 will satisfy your theorem, and in that sense, it can be considered as pseudorandom. Question?
I want to just address this point.
Yeah, please.
At least from the complexity theory point of view, we usually look at Boolean functions, and when we look at Fourier transform, we map true to -1 and 1 and false to 0 to 1. So 0 would represent not having a value, so the 0 function just wouldn't be considered. And then for this special case, what the pseudorandomness means is that the function, predicting the function has no parity of the bits is a good predictor for the function. So the value of the function sort of fools any linear test of the inputs. So in that sense, it's pseudorandom in the sense that Luca was talking about before, and that this function, in some sense, fools any kind of linear test.
Okay, so as I mentioned, there is a close connection between the Galois U2 norm and Fourier analysis. In fact, they are more or less equivalent. So let's establish that. So what do I mean? There is a connection. So the connection is that the U2 norm of a function is the same as the L4 norm of the Fourier transform. So by the way, I should say that, again, there is an analogy that can be made with graph. So one should think of these averaging over these parallelograms as something similar to counting the number of 4 cycles in the graph. And that lemma is then similar to the lemma that David presented, that the number of 4 cycles is the same as the sum of the 4th powers of the eigenvalues. Okay, so let's quickly prove that using the basic properties that was just erased. So we'll just use the definition of the U2 norm. So if you look closely at what the average is about, so this is the average over A, B, C, and D with the condition that A plus B equals C plus D, f of A, f of B, f of C, f of D. So I'm making a substitution of A equals to X, B equals to X plus H1 plus H2, C equals X plus H1, D equals to X plus H2, and the condition A plus B equals to C plus D is the only relation between them. And this is exactly the same as the inner product of the convolution of f star f with itself. If you remember what the definition of the convolution is and what the definition of the inner product is. And this by the isometry of the Fourier transform. This is the same as the Fourier transform of f star f, inner product with itself. And by the property about convolutions, this is the f hat squared, inner product with itself. And this is exactly the fourth power of the L4 norm of f hat. That proves the lemma. Okay, so I'm just going to again quickly tell you about the connection between L hat infinite norm. I have shown that the U2 norm is the same as the L hat 4 norm, but it turns out to be they are more or less equivalent. So I guess this is a corollary, but it's I'm still going to call it a lemma. So if f is one-bounded, then the L infinite norm of the Fourier transform is at least the square of the U2 norm, and at most the U2 norm. Okay, so now I just want to make one point about the U2 norms that I should have made, which would make things clearer, I guess. So if f is one-bounded, then we have the trivial bound that the U2 norm is at most 1. And this bound can clearly be obtained because, for example, your function can be the constant function 1, and the U2 norm would be exactly 1. Now, if your function f is random, take a random -1 +1 valued function, for example, then you can easily convince yourself that its U2 norm is small, certainly little of 1 for random f. So somehow the idea should be that your quasi-random objects should have small U2 norm, or otherwise it should have some structure that prevents the U2 norm from being small. And this lemma is going to say that the smallness of the U2 norm is going to be more or less equivalent, at least qualitatively, to the smallness of the L infinity hat norm. Okay, so this is going to be just a quick consequence of this lemma. So if I look at the U2 norm to the fourth power, this is the sum of f hat of r to the fourth, and this is clearly at least just pick one coefficient out of it. It's at least f hat, the L infinity norm of f hat to the fourth. So this established one side. Question?
Do you mean in the U2 to the 4 expression, do you not mean the hat on the f?
Yeah, thank you.
And in the line as well?
Yeah, thank you. Right. This establishes the right side of the inequality. And for the right side, the following, and this is something that's often done in Fourier analysis. So I pull out 2 copies of f hat. And then what is remaining is the L2 norm of f hat. And now by the Parseval identity, the L2 norm of f hat is the same as the L2 norm of f. And because f is one-bounded, this L2 norm is at most 1. So this establishes the left side of the inequality. So to finish the story about the connections between Galois U2 norm and Fourier analysis, let me just state something, which is just this lemma restated. But it has a significance in the theory. So this is usually referred to as the inverse theorem. in this case, for the Galois U2 norm. So here is the statement that f be one-bounded if its U2 norm is at least delta for some positive delta, then f hat of r is at least delta squared for some r. So in other words, f correlates with the linear phase. The linear phase being the phase defined by r. So this only uses this left-hand side of the inequality. So let me just quickly explain what is an inverse theorem. So in this type of theorem, we want to understand what is obstruction to uniformity. So as I said, a random function is expected to have small U2 norm. This is trying to understand for what type of functions you have large U2 norm. And the conclusion is saying that the linear characters, the linear phases, functions of this form are obstructions to infinity. Because every function that every function that has large U2 norm is going to be correlating with 1. Now, this is a very simple statement I just deduced quickly from basic facts about Fourier analysis. But one can ask similar questions for the higher Galois UK norms, which would be useful for more complicated arithmetic problems. And those inverse theorems are a great, has a lot of research. And in particular, there is no easy proof, and there is no quantitative proof. So things get bad for k, perhaps okay for k equals to 3, but certainly bad for k at least 4. And I'm sure Julia will say something about them. Okay, so I've spent all this time talking about Fourier analysis and Galois U2 norm. So they are going to be measurements for pseudorandomness. Okay? So now I think it's time for me to state what the actual regularity lemma is. In fact, I'm going to have to start with a weak version of the regularity lemma. So this is just going to be a precise statement of what the rough form was previously. Right, okay. So before I state that, I have to define a few things. So this is called factors. So I'm afraid this is just a piece of nomenclature that will be very useful in the statement of the theorem and its proof. So a factor, which will be denoted by script b. You may or may not always tell whether it's a capital B or a script b, but there will be no capital B appearing elsewhere in my lecture, so a b is always a script b. So a factor b on G is just a partition into disjoint subsets. And these subsets are called atoms of B. And if I have two factors, B prime and B, I say that a factor B prime is a refinement of B in the obvious, when the obvious thing happens. If a factor B prime is a refinement of B, if so you have B, that's like these are atoms, and it's B prime is a refinement when it's like this. So the atoms of B prime, when the atoms of B prime are subsets of the atoms of B, then it's refinement. exercise fitting this sentence. Now, an important notion is the notion of conditional expectation. Expectation of a function with respect to a factor. So this is a new function defined by its value on x is going to be the average of the values of the function f on the atom containing x. The average of f of y, where y ranges over b of x. B of x is the atom containing x. Okay, so when you have these atoms, you have a function f that could take different values on these atoms. What the conditional expectation does is that it makes the values on each atom the same by taking the average on that atom. So in particular, you'll see the connection between this and the structured part that was mentioned earlier. If these were cosets of subspaces, then this conditional expectation will lead to those structured pieces. So in fact, that's what I'm going to do now. I'm going to define linear factors that are factors whose atoms are cosets of subspaces. And these linear factors are the only type of factors that will occur in this lecture. So that R1 to Rk are frequencies, so they are elements of G. Then the linear factor defined by them is the factor. The linear factor B defined by them is the factor whose atoms are cosets of the subspace defined by these k frequencies. So this subspace is a set of vectors orthogonal to all of the i's. So if these k frequencies, k vectors, are independent, linearly independent, then we define the dimension of the factor, the dimension of the linear factor, to be k. So there's nothing complicated going on there. So all that's happening is that you have these, this is a subspace, and these are cosets, shifts of this subspace. The subspace is defined by these k frequencies, R1 through Rk. So all of these subspaces have codimension k, and this is the dimension of the factor. And just to note, the number of atoms is 2 to the k. So you should think of this dimension as some sort of thing that measures the complexity of the factor. So of course, the smaller the number of atom is, the simpler the object is. And the number of atom is 2 to the k. So the smaller the k is, the simpler the object is. Any questions about the definition? So I'm now ready to state the weak regularity lemma, but before I do that, I just realized that I promised somebody in the audience that I'll say something about this, say something else about this inverse theorem for the U2 norm, and I forgot earlier, so here it is. So what I'm about to do is to develop the regularity lemma, basically using this inverse theorem for the U2 norm. But there are already a lot of results and applications one can prove simply using this. For example, the proof of Roth theorem about finding 3-term arithmetic progressions in dense sets of integers. It can be proved using this simple Fourier analysis theorem, the inverse theorem for the U2 norm, together with the density increment argument. But the point is that there are a lot of other applications, which is this inverse theorem by itself is not enough. And that's why it is useful and important to develop the more precise regularity lemma that I'm about to discuss. So let f be a one-bounded function. So this is the arbitrary function that we're going to decompose into a structured piece and a random piece. Then there exists a linear factor b with dimension at most. Okay, so let epsilon be a positive parameter. There is a linear factor b with dimension at most epsilon to the minus 4, such that we have the decomposition f equals to the conditional expectation plus an arrow g, with the U2 norm of g being small at most epsilon. So the conditional expectation is viewed as a structured piece because this is b is a linear factor, and this conditional expectation is going to be constant across each coset. And then the g is pseudo-random in the sense that its U2 norm is small. So this bound on the dimension or the complexity is important because without this, every function is structured, because you can take the factor that's whose atoms are just one element sets, and every function is going to be structured in that way, and it doesn't help. Any questions about the statement?
So just check your things. For any function that is 2 to the 1 over epsilon to the 4th kind of sets and constants, such that every f is, I just want to make sure what is the interpretation. So the first term means that the function is, there are 2 to the 1 over epsilon to the 4 constants.
Yeah, exactly. So the k is going to be epsilon to the minus 4. So I can take at most epsilon to the minus 4 of these frequencies that define a subspace of codimension epsilon to the minus 4. And your constant, this structured piece, will be constant on all cosets of it. And the number of such cosets is 2 to the epsilon to the minus 4. The point is that this is so when epsilon is a constant, small constant, this, whatever it is, it's also a constant. Now, you should also have the question about why this is called weak. So it is weak because that how small the U2 norm is allowed to be is too large compared to the complexity of the structured part. In a lot of the applications, I will get some kind of lower bound when studying this structured piece, and the lower bound will depend on this complexity. And then I will need to show that this pseudo-random part makes a negligible contribution. But when the pseudo-random part has like U2 norm at most epsilon, sometimes this isn't negligible at all for when I apply. And this is the reason why it's called weak. But it's all right because it turns out that we can iterate this procedure to get a strong regularity lemma, which is the regularity lemma that I'm actually going to use to prove the removal lemma. So in the last 5 minutes, I'm just going to state the strong version so that you could compare. So, right, I should do that over here. Okay, so again, I have some epsilon, but now I'm going to also give myself a growth function, omega. This is just going to be an increasing function. That's what I meant by growth function. And just to be clear, it's allowed to depend on epsilon. Okay. So let f be one-bounded. Then there is a linear factor. B with dimension bounded in terms of the two things you give me, epsilon and omega. Such that I have the decomposition. There is a structured part. Now I will have two pieces of arrow. The first piece of arrow is called SML, denotes small. And the second piece of arrow is this. PSD denotes pseudorandom. So we should think of FPSD as a pseudorandom piece. And this F small denotes a small arrow that has to be there, and we just have to deal with it. Such that you have this decomposition with, so the small term is supposed to have small L2 norm. And the pseudorandom term is supposed to have small U2 norm. And not just small, but very, very small. And what I mean by very, very small is that it's very, very small even compared to the complexity of the structured part. So the complexity of the structured part is basically the dimension of the linear factor. And my omega is a pre-chosen growth function. So omega of the complexity could be very large. And when you take the inverse, it could be very small. So it's extremely small even compared to the complexity of the structured part. And this will turn out to be enough in applications because you just choose your omega to be growing rapidly enough so that this is indeed an arrow.
So yeah. Just a syntactic question. So I assume the fact that it's a linear factor is somehow important. So for example, if the function is Boolean, like -1, 1, then I assume, so, you know, without linear factor, the weak regularity lemma is a triviality, but I guess linear thing makes it interesting. So maybe can you comment on the importance of linear factor as opposed to any factor?
So the linear factor is certainly something that's important. It's something what you get from the proof. But I think what is most important is this complexity bound. Without this complexity bound, any function can be written as a conditional expectation.
No, but for example, assume the function is Boolean.
Yeah.
I can just say, okay, let's partition the space into x's where the function is 0 and x where the function is 1. It's not a linear thing, but it's like its dimension is 1.
Yes.
It's fantastic. So assume in applications linearity is important?
Yeah, exactly. In applications, you will be using the fact that there are linear factors.
Is there some intuition or it's unclear? We'll have to wait.
So the intuition is exactly that this is related to the inverse theorem. In the inverse theorem, the abstractions to U2 uniformity is correlation with linear factors. And these linear factors are exactly functions that are constant on linear subspaces. Now, as Julia will discuss on Thursday, when you go higher order, for example, U3, then there are more abstractions. And when there are more abstractions, you have to allow more structured functions. And to do that, you have to introduce a more general class of factors or a more general class of structured functions. But for the case of U2, this is enough. Yeah.
Can you say again, what is the upper bound on dimension of B?
So this is just a constant depending on the two parameters epsilon and omega given to me. So O of 1, but the implied constant depending on epsilon and omega. Any other questions? Yeah.
So I just want to address Penny's point, which is that the linearity is, the linearity of the factor is because U2 form measures correlation with linear tests. So you get something similar for any kind of class of tests. Although, okay, there's one nuance here. For a general class of tests, you'd get like decision trees. The factorization would be a decision tree that makes queries according to these tests. Here, it's not just a linear decision tree, but an oblivious linear decision tree where you're making the same queries along every branch, which I don't think you get in general. But pseudorandom. But the point is that the kind of factorization that you get, the decision tree that you get, is going to be in terms of the same class of functions that you're trying to define pseudorandomness against.
Any other comments?
So just to be a little bit more explicit, for the constant that depends on epsilon and omega, as long as omega is at most a constant tower growth, this is going to be a tower.
Yeah, so from the proof, we will see tomorrow that this constant will be the function omega iterated epsilon to the -1 times, essentially. So in a lot of the applications, you're forced to choose the growth function omega to be exponential. And that is why, in that case, and when you use the regularity lemma, you will get a bound of tower type. So I think David mentioned that in a lot of the applications of the graph regularity lemma, you get tower type bounds. It's the same situation here. So tomorrow I will prove these things. The weak and the strong regularity lemma and the deduction of the triangle removal lemma from it. Yeah.
So how should I be thinking of f small?
Yeah.
The Fourier transform of it will also have a small L2 norm. It'll be equal, right?
So perhaps one thing that helps is that something I forgot to mention. So these UK norms, they are nested in the following way. So they are increasing, and right. So I believe you can even put. So it's certainly the case that you can have bounded by L infinity, and maybe it's also bounded by L2, but forget about that. So the point is that for example, requiring U3 norm to be small is a much stronger condition than requiring a U2 norm to be small. And this was needed because in applications, we need sometimes a stronger notion of quasi-randomness. And now about this L2 norm, you should think of requiring the L2 norm being at most epsilon is a much weaker condition than requiring the U2 norm being epsilon. And that's why even though this epsilon may not be may not be small enough, but in applications, you are often can deal with this. But what is most important is this part. You should naively, roughly just think of this as in something that just come along, but you can deal with it. But this is the real meat of the strong regularity lemma. Okay. I think that means we're done for the day, if I may say so.